So the next invited speaker is Professor Herman Kamper. He's an associate professor at Stellenbosch University, South Africa. He has been working on speech representation with minimal label data for a very long time. And he's a pioneer of learning speech representation. Herman, now the stage is yours.
Thanks so much. Can you hear me?
Yes, I can hear you.
Excellent. Thanks so much for having me, and thanks for the cool previous talks. I really enjoyed the keynote and also Dang Chi's talk. So I'll be talking about some recent work that I've been doing on unsupervised word segmentation from speech. I've been working on this problem for quite some time. So maybe if you've seen a previous talk, you'll have seen this slide. But basically the problem is you want a model that can take a corpus of unlabeled speech audio. You don't know the language, you don't know the words, and you want the model to infer where words start and end in the speech stream. And if we could do this, then this could allow speech technology in languages where it's very difficult to get labeled data. And it can also be used as a way to investigate how infants acquire language from their surroundings, which includes a lot of unlabeled speech audio. So what I'm going to talk about today is one particular approach to this problem. And it's actually a relatively old methodology, but with some new models. So basically the methodology works like this. You start with your unlabeled speech audio, and then you use some unsupervised acoustic unit discovery method to transform that unlabeled audio into a sequence of discovered phone units, basically clusters that you hope represent the phonetic inventory of that language. And then what you do is you feed the sequence of basically cluster IDs, these discovered phones, into a symbolic word segmentation method. These are methods that try to look for repeated patterns in these discrete symbols, and then in some way basically propose boundaries between these discrete symbols. And if you do this, basically start with a bottom-up acoustic unit discovery method, and then apply symbolic word segmentation on top of those discovered units, then implicitly what you get is you can, from this combined approach, you can infer where words start and end. So what I'm going to do is, so this idea is pretty old. They used that at the Johns Hopkins University workshop in 2012 already. But what's new in this talk is basically I'm going to talk about two new techniques, one for unsupervised acoustic unit discovery and one for symbolic word segmentation. And then I'm going to glue them together and see what happens. So first I'll talk actually about the top part, the unsupervised symbolic word segmentation method. So imagine you've got an auto-encoding recurrent neural network. This is a model that has an encoder and a decoder. And what the model tries to do is you've got the encoder that reads in a sequence of symbols, and then the decoder tries to decode those same symbols. For this part of the talk, I'm just going to replace my acoustic units with letters, but you in your head, you just map them to acoustic units. So we've got this auto-encoding RNN from somewhere. I'll tell you in a bit where it comes from, but let's just think it exists. And this model can maybe encode some sequence as well. Maybe the word time is encoded well in the model. And we can actually measure how well it encodes this sequence by taking the product of the output probabilities of this model. If we feed it with some other sequence, maybe a word like ongti, which isn't a valid English word, then maybe the output probabilities are lower because the AARNN doesn't model this word well. And we can use this property that some words are encoded well, others are not encoded well, to actually segment symbolic input. So let's say we've got a sentence like this one, a long time, but there's no spaces in between the words, we don't know. What I can do is I can propose a segmentation. Let me propose a segmentation like this. So I propose that this sentence consists of these 5 words. What I can do is I can feed in the first word into my AARNN and get an output score for that segment. And I can do that for each of the other segments. So for each of the 5 segments, I get a score for that, for each of the segments. And that can give me an overall score for how good is the segmentation given my auto-encoding RNN. Okay. I could have proposed a different segmentation, maybe this one. Okay, and again, I could feed in each of the individual segments into my autoencoding RNN and get an overall score for how the segmentation, what the segmentation looks like. So the question is this segmentation better or is this segmentation better? And you can ask the AERNN according to your parameters theta, which one of these two are better. Now, if we believe we have some RNN that can do this, then this just becomes a dynamic programming problem. We're trying to find, out of all the possible segmentations, we're trying to find the optimal segmentation for this utterance given the model. And that's what that second DP stands for in DP-DP-AERNN, and the second DP stands for dynamic programming. The first DP stands for duration penalized. So there's actually a trivial hack for most models. So if you have an AERNN that just places a large weight on the first input, then this model will tend to just put every single symbol, every single character in a word of its own, and that's not what you want. So we include a duration penalty to encourage longer words. Okay, cool. If we do that, amazing. Then we can just solve this whole thing with dynamic programming. And if we, for instance, say like all words needs to be 4 characters or less, then that corresponds to finding the shortest path through a directed graph, such as this one. Each of the edges in the graph will then be given by your AERNN. So we just take the negative log likelihood from the AERNN for that segment. And then also, importantly, we add the duration penalty. So W duration is the duration penalty. I use a very dumb duration penalty. It's just a linear function that penalizes short segments. I also, in the paper, I'll tell you what the paper is in the end. In the paper, I also try a probabilistic prior where I basically penalize the duration probabilistically. Okay, so given you've got the segment score and you've got your duration penalty, then this whole thing just reduces to finding the shortest path. One path could be the red path and you score that with your models. Another path could be the blue path. You score that with your model and the problem becomes finding the shortest path through the graph. Okay, really easy. There's one major thing. I started by saying you just need to believe me that there is this AERNN. Where does this come from? You know, where does this autoencoding RNN come from? There's a few different approaches. The one idea is to iteratively refine the autoencoder RNN. So you start with some random segmentation. You just put boundaries randomly between symbols. Then you train your AERNN with those random segmentations. Then you do dynamic programming duration penalized segmentation, which gives you a new segmentation. Then you retrain your AERNN on that new segmentation. Then you segment again and so on. Okay, you get the idea. So that would be one option. The other option is to use a probabilistic approach to sample segmentations. And this might allow you to explore the space of possible segmentations a little bit better. And Micha Elsner and Corey Shane, they actually proposed a model like this where they probabilistically sample segmentations. I should say that their approach massively inspired my model, and my model can almost be seen as like a simplification of their approach. Okay, so 2 ideas for the AERNN. I tried the first one, I tried it. The second one I also tried, but I really struggled to get it to work on top of discovered units. So then I did the dumbest thing that I could think of, which is just to train on full utterances. So I take a full utterance, I encode it with some model, and then I train the AERNN just on these full-length utterances, and then I do segmentation using that AERNN. And this seemed to work pretty well. Okay, that was super quick. Sorry if I'm going a bit fast, but so that's a kind of new-ish model, heavily inspired model for unsupervised symbolic word segmentation, which operates on discrete symbols. Now I'll talk a little bit about another approach for unsupervised acoustic unit discovery. So going from the speech signal to these discrete units. This is joint work with my PhD student, Benjamin van Niekerk, and we presented this at Interspeech last year. And what you'll see is actually this is also just duration penalized dynamic programming, but with a different scoring function. Okay, so it won't look like that in the beginning, but after a while, we'll see that it's the same thing. Okay, so how this approach works is you start with some self-supervised speech model, think a CPC model. And this takes in speech and then outputs continuous feature vectors across the speech sequence. What we're going to do is we're going to quantize these continuous vectors using some learned codebook, where you basically try and assign each of the continuous features to the codebook entry that's closest to it. But instead of assigning the vectors independently, we're basically going to constrain them so that they're assigned in blocks. So if I propose a segmentation like that one, then each of the frames within one of these segments needs to be assigned to the same code. So I hope that makes sense, but look at the third segment there. There are 3 frames, and they're all assigned to the orange code. So if I propose a segmentation, then that whole segment needs to be mapped to a single code. I could have proposed a different segmentation, same input, and then there would be a different assignment of the blocks to each of the codes. Okay? And the problem then becomes finding the best segmentation. And how we basically score a segmentation is by calculating the sum of the square distances to the codes. In other words, the sum of the square distances of the arrowed lines in this figure. Okay, and the result is that if we pick the segmentation on the left, for instance, which is the best segmentation between these two, then you'll encode that sequence according to the clusters, the codebook entries to which it's assigned. How do you find the best segmentation? Again, we're going to use dynamic programming, but now we're going to score the different segments using this CPC clustering model. And also, again, we're also going to add a duration penalty. We need a duration penalty because otherwise it will just end up putting each frame into a code of its own, which is not what we want. Okay, so we solved this exactly like we did before for the symbolic word segmentation, but instead of characters, we now have continuous feature vectors. And instead of using an AERNN to score a segment, we now use the sum of the square distances to the code to which that segment is assigned. And then again, we solve it with dynamic programming. The duration penalty actually that I use for this is the same has the same shape as the one that I used for symbolic word segmentation. Okay, so I've very quickly introduced a new approach for unsupervised acoustic unit discovery, and I've proposed an approach for unsupervised symbolic word segmentation. And what I'm going to do now is I'm basically going to do this together. As I've mentioned, this is an old idea, this kind of idea of taking bottom-up discovered units and then applying symbolic word segmentation on top of it. People have tried it before, but not with these exact models. This is one approach. I think since the 2012 Johns Hopkins workshop, most people have actually gone another route, which is to train one joint model for both of these tasks together. And what I'm going to do is I'm going to compare this bottom-up discovery followed by segmentation with these joint approaches. So 2 very recent joint approaches that work really well is the segmental CPC model and the multi-level aligned CPC model. I think some of the authors on these papers are also speaking at this workshop. So both of these models, I'll try and do them justice, both of them start with a bottom CPC layer, which tries to learn something like foam units. Then both of them have a differentiable boundary detector. And then they've got an upper layer, CPC layer, which tries to model something like words. And in both cases, the whole thing is trained jointly. This means that the things that get learned on the word layer, the upper layer, can actually influence the acoustic units at the bottom, the phone layers. So this is in contrast to what I do. In my approach, the phone discovery happens and then you're doing word segmentation, and the word segmentation actually doesn't influence the phone layers. I'm not saying my approach is actually better. I'm not arguing that it's superior, but you'll see in a second that it does give relatively good results, and I think therefore it should be considered. So these are actually the results on the Buckeye English data, and I'll just go from the bottom to the top. So the bottom line there, that's the chained approach, where you first do CPC plus k-means with dynamic programming duration penalized to get acoustic units, and then you do the DP AERNN on top of that to discover words. The 2 models above that, those are the 2 CPC models, and you can actually see that a precision and R value, the multi-level aligned CPC model does best, but this chained DP approach actually does better on recall and F1. Very quickly, the 2 models at the top, that's some of my older work, which basically tries to get away from modeling phones entirely And what they do is those models just model whole words directly, but you can see that the other approaches tend to perform better. I also applied my chained DP-DP approach to the Zero Speech 2017 and 2020 evaluation data for track 2. And you can see there that we actually get some of the best scores for these tasks, best reported scores on this evaluation benchmark. What are the types of words that this model does well on, and what are the words that it struggled with? So here I show on the top part of the plot word types with the highest recall according to the evaluation. And then in the bottom plot, I show examples of words that are not segmented well. And if you read through the word types here at the top part, you see that there's a lot of shorter filler words that are segmented well. While the words that this model struggle with is typically longer words, longer content words. And you'll actually see that there are many words ending on "ly" at the end. So basically, actually, exactly. And what happens there is often the system puts a boundary in the phone that precedes the "ly" phone sequence. So it puts a boundary there. It's a little example of how that happens. Here's one segmentation. The top codes, the numbers at the top, that is the acoustic units discovered by the DP-DP method. And then the dark black lines are the word boundaries proposed by the autoencoding RNN DP-DP. And you can see it does relatively well. But if you look at the last word, weekend, you can see that it gets the first boundary right, but then it actually splits this word into two parts, week and end, which is maybe not unreasonable. This is my last slide. So I think the takeaway here that I hope is that bottom-up acoustic unit discovery with subsequent word segmentation is a competitive approach. And it's something that we shouldn't maybe disregard. It could maybe be a way to, because there are a lot of questions about how infants actually do this. Do they do it in a bottom-up way, or does word segmentation help them discover better units? There are a few improvements to the DP-DP approach itself that should be considered. My duration modeling is super coarse. It's not that well. And my model can't actually do lexicon discovery. So it can tell you where words start and end, but it doesn't build up an explicit lexicon. Taking a step back, it's cool that we're getting good results, but the absolute results are actually still pretty low. Word token F scores of 25%. And the other interesting thing is, although my methodology is so different from the others, the joint approaches, we're getting pretty similar scores. So maybe we are reaching the limits of what we can do just from unlabeled speech data. And maybe it's starting to get important to include higher level signals from maybe other modalities, maybe the Ego 4D data set that the keynote talk spoke about, to actually incorporate that top-down signals. And we know that infants have access to cross-situational cues when learning language, and robots have sensors that's not just audio. Very quickly, the paper is on arXiv. I put that up last week. And then I've got two repositories. The one is just for the DP-DP AE-RNN, which is also applied to phonemic sequences. And then I've got the VQ WordSeg, which is a very messy repository, taking everything that I spoke about together. Thank you so much, and thanks to the workshop organizers.
Thank you, Herman, for the excellent talk. Okay, we will have the Q&A after all the invited speaker.